Hello everyone. In this video, we're going to look at an artificial neuron, also known as Perceptron, that is modeled in an Excel sheet. Artificial neuron or Perceptron acts like a biological neuron, and they can be trained to perform deep learning. They are foundational concepts of modern artificial intelligence technology, and we will provide the artificial neuron with two binary inputs and train it to perform some useful outputs. In this Excel sheet, I have a representation of a biological neuron. We have talked about this biological neuron in the previous video, and next to the biological neuron is the artificial neuron on an Excel sheet. It has inputs, weights, bias, summation node, activation function, and output, pretty similar to the electrical circuit that we saw in the previous video, and that is as well comparable to the biological neuron. The other representations in this Excel sheets are I1 and I2. They are nothing but the inputs. They are binary in nature. P1, P2 refers to the actual perceptrons. P out is the end layer perceptron that makes the decision. W is the weight, and weights are provided in different layers. So in this case, this weight value represents from input 1 to perceptron 1. Similarly, the next one shows that the weight value represented here is from perceptron 1 to the perceptron output layer. Bias is just shown as bias. AF1 refers to the activation function on the first layer of this perceptron, and TH refers to the threshold value. F denotes the activation function, and AT on the subscript of the F denotes the threshold value of the function. P out is the perceptron output, that is a last layer perceptron, and the function threshold on that particular perceptron. The summation is between the input and the weight. They are multiplied together, and that has been added with the bias value. The activation function used is simple if logic. When a condition is met, we get the true value. If the condition is not met, we get the false value. Let's go into the actual simulation now. And with a two input binary perceptron, the best thing to simulate is to reproduce the logic gate equivalent. There are some basic logic gates like we saw in the previous video, and we will try to simulate these gates in this Excel perceptron model. And we will start with the AND logic. There are two different models here, and they only differ based on the weights and the activation functions used. While we simulate the model, I will show differences between these two models. And with the AND gate logic, it should produce an output when both these inputs are turned 1. 1 meaning high, 0 meaning low in binary. Let's test these perceptrons on the truth table that is shown here and see what's going on. The table below is nothing but the input values, the weights, the bias, and the activation function and its threshold value shown here. So in this model, I've connected model 1 and model 2 together on the input layer so that I can, when I change one, both the model input values change at the same time. So I'm going to change the input on the model 1 and 2 to 0 to show that the output is 0. So here is the output, and the output has the activation function. Just before the output, we have the summation node where the input is multiplied by the weights and added to the bias. And next to the function, I have the actual formula or the condition on the activation function. So here we can see that the activation function uses 0.5 as the threshold value. Whenever the summation node becomes equal to 0.5, we should see this activation node turning 1, otherwise 0. So I have also provided another table below, just below the perceptron, to show that for each of the AND gate logic, based on the inputs we provide, what is the actual value that we see on the summation node, comparing that with the threshold, whether the perceptron activates and then fires to provide a 1 on the output or not. With the 0 on both input nodes, we see the summation is 0. 0 is less than 0.5. Therefore, the truth on this logic should be 0. Because this condition is not met, therefore we get a 0 on the output. On the other hand, in the model 2, we see that the weights are different. That's because the activation function is different and the threshold value is different as well. So here the activation function compares whether the summation value is less than 1. If that is true, then we get a 0. This is inverse to the logic that we have on model 1. And if not, it will provide 1 on the output. Therefore, to satisfy this condition, the weights and the bias should be tuned accordingly. And because the threshold value is 1, we have weights 0.5 on both W1 and W2. And here in this model 2, because inputs are 0, the summation value is 0, and 0 is less than 1. If that condition is satisfied, then the output should be 0. So we get a 0 on the output. Although the activation function and the threshold value and the weights are different, we still meet the AND gate logic requirement on model 2. Let's go to inputs and then change that to the next values. So I will turn input 1 to 1, and then we see that we get 0.25 as the summation output. 0.25 is still less than 0.5, and therefore model 1 perceptron does not provide a 1 on the output. When we go to model 2, we get a summation value of 0.5, because 0.1 multiplied by 0.5 produces 0.5 on the output, and 0.5 is less than 1. That condition is met. If the condition is met, the answer should be 0 as the value. So we get a 0 on the output node on the perceptron. Okay, now let me turn input 1 to 0 and then input 2 to 1. Okay, now it's just the other way around. Again, we get a 0.25 on model 1 summation node and 0.5 on the model 2 summation node. Still, the condition has not changed from the previous state, and then they produce 0 on output perceptron. Now the last combination is 1 on both the input 1 and input 2. So now what has changed? You see the summation node is 0.5, which is equivalent to the condition. So the condition is met and it provides a true value on the output, which is 1. So this perceptron provides satisfied the AND gate logic. Let's go to model 2. In model 2, we have 1 on the summation output. 1 is not less than 1. 1 is equal to 1. Because this condition is not met, we get the false value, that is 1 on the output perceptron. Therefore, all the 4 logics or four states of this logic gate are satisfied. Therefore, this perceptron is trained to behave like a AND gate. The next one that we are going to look at is OR gate. OR gate and buffer are pretty similar that we saw in the previous video as well. The buffer is nothing but it produces the input values on its output. So on the OR logic, again, we have two models here. One model has a different activation function, threshold value, as well as the weights compared to the model 2. So in the model 1, let's try to change the input values based on the truth table that we have on the left. And let's see if the perceptron behaves as it should be, and what changes do we see within the summation node and the activation output. Let me turn this input 1 and input 2 to 0. So when both inputs are 0, we see that the output on both the models are 0. If I turn one of the inputs to 1, we see both the models produce 1 on their outputs. Let me turn input 1 to 0 and input 2 to 1, again we see that the outputs have 1 on their output values. If I turn both these inputs to 1, now again I see the output value is 1. So let's understand when we let me go back to the initial state, that is 0 comma 0 on the inputs. So when I have input as 0, the summation node is 0. The first model has a condition: if sum is greater than 0.24, then the true value should be 1. Now 0 is not greater than 0.24, therefore we get a false value, that is 0 on the output. On the other hand, on model 2, we have summation output as 0, which is less than 0.5, and therefore the true value is 0. Now when I turn input 1 to 1, now the model 1 has a summation output of 0.25. 0.25 is greater than 0.24, which is the threshold value, and because it has exceeded the threshold value, we see the true value output, that is 1 on the Perceptron 1 model output. On the model 2, now we have that the summation node is zero point 0.5, whereas zero point 0.5 is not less than 0.5, they are equal. Because this condition is not met, the false value 1 is shown on the output. Well, if I swap these inputs to 0 and 1, we will see the same behavior: 0.25 on model 1 perceptron summation node and 0.5 on model 2 perceptron summation node. When I turn both these inputs to 1, so model 1 has now 0.5 as summation output. So 0.5 is greater than 0.24, and the true value for this logic is 1 on the Perceptron 1 model output. Whereas in Perceptron model 2, we have the summation output as 1, and 1 is not less than 0.5. So this condition is not met, and if the condition is not met, the true value, the false value that should be on the output is 1. So that is what we see on the output. That is how our logic works on a perceptron. Now let's say the perceptron has migrated from AND logic to OR logic on the Excel sheet. Now let's now go to the NOT logic. I will just take one of the model and explain how it works here, and then we'll move on to the other logics. The NOT logic is simply to say the output should be the inverse of its inputs. Where the inputs are 0, we see 1 on the output, and when the inputs are 1, we see 0 on the output. Same thing, when the inputs are 1, we see 0 on the output. Let me turn the both input 1 and input 2 to 0, and now we see that the summation node is 0.25, and the condition that is applied on the activation function is if the summation node is greater than 0.25, then we get a 0, otherwise 1. Now 0.25 is equal to 0.25, neither great nor low. Because this condition is not met, we get the false value 1 on the Perceptron model 1 output. Perceptron model 2 is similarly designed. Now let's check the next truth table logic, that is 1 on the input 1. Now we have 0.5, and 0.5 is greater than 0.25, therefore the true logic out value, that is 0, is shown on the Perceptron output. If I turn input 1 to 0 and input 2 to 1, we will see the same value on the summation node 0.5, and again we don't see any output on the Perceptron out. Now if I turn both these inputs to 1, now the summation value is 0.75, which is greater than 0.25, therefore the true logic condition is met, and the output should be 0 in this case. And that is what we see on the Perceptron 1 model output. Same thing is happening on the Perceptron 2 model. I've just not gone into the details. Now let's move on to the next logic gate, that is NAND logic. NAND logic is nothing but not an AND. We see that output on the NAND logic is inverse to the AND logic. And let's try to simulate this gate with 0 on input 1 and input 2. So in this case, please note that the weights are negative to show the inverse on the AND gate. Now, because input 1 and 2 are 0, we see 0.5 that is coming from the bias. Earlier in the AND gate and OR gate, we did not have any value on the bias, but here we do have a value on the bias. So, and the bias value is the only one that is on the summation node. And the condition here is that if the summation node is less than 0.25, then the true value is 0, otherwise 1. 0.5 is greater than 0.25, therefore we see the false value on the condition, that is 1 on the perceptron out, and that is exactly what we need on the truth table. Now let me turn this input 1 to 1, and now the summation output is 0.25. 0.25 should be equal to 0.25, but however the condition is less than, therefore this function value is false, and the false value on the function is 1. That is what we see on the output. Next, let's change the input to 0, 1, and input 2 as 1. And in this case, again, we see 0.25, which is neither less than 0.25 or not greater than 0.25. Therefore, that condition is not met, and we see the false value 1 on the output. When I change both inputs to 1, now the output that is on the summation output is 0, because 1 multiplied by 0.25 on both inputs added with the bias will get a 0 on the summation, and 0 is less than 0.25. That is a true condition, and for the true condition the output value is 0. So this perceptron works as a NAND gate. Now the next logic that we have is a NOR logic. So NOR logic is the inverse of OR logic, and NOR logic should only provide an output 1 when both the input 1 and input 2 are 0. And let me try to do that first. Both inputs are now both the inputs are set to 0, and we see 1 on the output. So here we have 0.25 as a summation output. 0.25 again is not less than 0.25. So the false logic on this output is 1. That is what we see there. So when I turn one of the input 1 to 1, summation output is summation output is 0, and here the activation function is now providing a true value, because 0 is less than 0.25. That condition is met, and the true value for that condition is 0. Same thing would happen if I change input 1 to 0 and input 2 to 1. We see summation output 0, so same state is maintained. Now when I change both the inputs to 1, we see that summation output is minus 0.25, and minus 0.25 is certainly less than 0.25, and the true value for this if logic is 0, and that is what we see on the output. So that is how all the gates work. That is how we train model a perceptron on Excel sheet. We can connect multiple of these perceptrons together to form a multi-layer perceptron and teach the perceptron to learn more complex problems and then solve those problems. Thank you.